All right, all right, all right. Here we go. Perfect. Let us begin our new section here, which is area. As we go through this, we'll try to go through at a nice, efficient pace. Hopefully, it'll make sense. You know what I mean? So, anyhow, let us go ahead and begin here. So, let's go ahead and read the question. Let R be the region bounded by the graphs of y equals square root of x and y equals x divided by 2 as shown in the figure above. Find the area of A. Well, this is a non-calculator active question, and in order for us to do that, we need to know which one's which. Well, I know this is a straight line, so that kind of tells me this has to be x divided by 2. And this here has your square root function, which is y equals square root of x. Now, if you were never unsure, oh, that's kind of bad. Here we go. If you've never unsure, plug a point. You know this curve here looks to be 2, 1. Well, which one can you plug in 2 and get 1? Well, obviously this one, because 2 divided by 2 is 1. So now I immediately know which one is which. Now we're in business. Find the area. We just want to find the area. Essentially, we just need to know what the length is, this length here, and find the area under the curve. Well, we just want this shaded region, none of this underneath here. So just top curve, which will give me the whole thing, minus bottom curve, and that'll give me what I want. So top curve minus bottom curve. So we're going to get the integral from 0 to 4, top curve minus bottom curve. Remember, this is all with respect to x dx. I'll go ahead and rewrite this to be x to the 1/2, and this will be x divided by 2 dx. So now that we have this, now that we have it rewritten, then we can take the antiderivative, and I might actually even do it on the corner here. X to the 1/2 is the same thing. Well, add 2 to 2. Add 1, which is 2 over 2. This is x to the 3 over 2. This is the antiderivative, so we're going to divide by that, and remember, we can bring up the 2. So this is going to be 2x to the 3 over 2 divided by 3. And what's the antiderivative of x? Well, the antiderivative is x to the power of 2 divided by 2, but notice how we already have 2 underneath, so we just put the 2 underneath with it, right? And that's pretty much going to be 4. If that's confusing, we can always rewrite this as 1/2 x, right? Then this is 1/2 x squared over 2. 2 times 2 on the bottom, that's where we get it, is 4. So we get minus x squared divided by 4. Let's put some parentheses around that from 0 to 4. All we have to do now is just plug these in, and we don't really have to plug in 0 because we're going to get 0. But anyways, we'll talk about that in a second. Let's plug in the 4. 4 to the 3 over 2 divided by 3 minus 4 squared divided by 4. Okay, I'll put a set of parentheses around here. Minus 0. 0, because if I plug in 0 to both of these, I'll get 0. Now, what is 4 to the 3 over 2? Well, remember, the 2 underneath means square root, which we rewrote here, or it also means what two numbers multiplies to give you 4. Well, that's going to be, I'll write it up here, 4 to the 3 over 2, that's going to be 2 to the third. 2 to the third is 8, right? So this will be 8 times 2, which is 16. So we're going to get 16 divided by 3 minus, well, 4 squared is 16 divided by 4. Now we need to find a common denominator because they're different. So we're going to multiply both sides by 3 over here, and we're going to multiply both sides by 4. 16 times 4 is 64 divided by 12 minus 48 divided by 12, which gives me 64 minus 48. That actually gives me 16 over 12. This can be reduced even further. I can divide both of these by 4. 16 divided by 4 is 4. 12 divided by 4 is 3. Boom. And I got my area there. Very good. Good. All right, let's go to the next one. Region R is the base of a solid. For this solid, the cross sections perpendicular to the x-axis are squares. Find the volume of the solid. So we need to find the volume, so we need an area model. Well, in this case, it told us it's a square. So we got these little squares in here, obviously of equal length. I know I didn't draw them perfectly, but we got these squares here of equal length. And the nice thing about the area of a square is that it's length times width, but they're both the same, right? Square has the same side length, so L times L, which is L squared. So if I want to find the area, that's 0 to 4. Well, what is your length? Well, your length is top curve minus bottom curve. So this is just the square root of x minus x divided by 2 squared dx, and we are in business there, right? So there is the setup for part B. We're not going to actually go ahead and solve this out. I just wanted to show you how we could set this up here, and then we'll be good to go. If you wanted to know maybe how to go about actually doing this by hand, it just takes a little bit of algebraic work, right? Which means we're going to need to do x to the 1/2, I'll rewrite it, minus x divided by 2 multiplied by x to the 1/2 minus x divided by 2, and then multiply this all out and take the antiderivative, but we'll say that for another day. Okay. This next problem here, C, write but do not evaluate an integral expression for the volume of the solid generated when r is rotated about the line, the horizontal line y equals 2. So we have our function here, which looks something like this. Boom. So let me grab that there. Okay, beautiful. And we're going to rotate this about the line 2. Okay, so how will this look like? Well, we're rotating it across this line, so it's going to look something like, ooh, I should maybe draw a different color. It's going to look something like this. And if we rotate it, it's going to look something like that, right? And we're going to get some kind of circular cone that looks like this, and ultimately we just want the volume of this here, right? So we're going to get a hole. So as you know, what we want to do then is we want to start at the line that we're rotating our function by, and we're going to do top curve, which is big R, minus little r, which is little r right here. Okay, why do we want to do that? Well, we're going to get a hole, so we want to get everything subtracted by the parts we don't want. Well, how do we get big R? Well, big R is 2, and we need to subtract this length. Well, where does that length come from? Well, that's 2 minus x divided by 2, and big R is 2. Big R is 2 minus this portion here. Well, what's this length coming from? Well, the square root function. So now we have, remember, this is it's forming a circle. This is why we're doing pi r squared. This is why we needed 2 different radiuses, because we're getting this circular motion. So we're going to get pi on the outside, 0 to 4, big R squared minus little r squared. Boom. I'll put parentheses around the whole thing, dx. There we go. And there is my setup. We're writing but do not evaluating. So there it is. Wonderful. All right, beautiful. Let's go ahead and move on to part D and E. So E, I'll do quickly, and then F, E we'll talk about, then we'll do E. I think E is a little more intuitive. So as we kind of get started with this problem here, we have the line x equals k dividing r into 2 equal regions, and we want to write an integral that's going to give us that. Well, if we're dividing this in half, I'm thinking there's a line here at x equals k that cuts this region in half together. Well, how do we write this, the integral that gives us that? Well, it's from 0 to k. 0 to k. Well, how do we get this area here to be equal regions? Well, top curve minus bottom curve. So square root of x minus x divided by 2 dx is equal to, that gives me the area of the right side, and then from the left side, and the area from the left side is k to 4, which is going to be top curve minus bottom curve, which is the square root of x minus x divided by 2 dx. Boom, there it is right here, my friends. That's going to give you the integral setup that'll get you that k value. All right, now let's go ahead and do the same thing, but now we're going to be grabbing this function, and it's going to be y equals k. So let's say some value y equals k, that's cutting this into equal regions, right? And this is with respect to k. So that means when we do our integral setup, it should be dy. It's with respect to y. So what does that mean about our equations? That means our equations need to change with respect to y. So we have y equals the square root of x, which is this function here, and we need to change it with respect to y. So let's solve for x. Boom, we get x is equal to y squared. And let's do it for the bottom curve. We have y equals x divided by 2, multiply 2 to both sides. Boom, we get 2y is equal to x. So there it is. Now we know bottom curve is 2y, top curve is y squared. So let's do from 0, we'll do it over here, from 0 to k, top curve, which is right over here, minus bottom curve, because it's with respect to y, so it will be 2y minus y squared, dy is equal to k to, well, if you put 4, you would be wrong, because it's with respect to y. So this goes from 0 to k, and now from k to 2. It's got to be 2. And it'll be top curve minus bottom curve, which is still the same. This curve minus that curve. So we're going to get 2y minus y squared dy, and there we go. And that's kind of it, my friends. Just kind of wanted to go through some basic ones. We'll go through a few more challenging ones together, but I do think area is a